All right, let's go ahead and get started, everyone. We can either have you come in, take your seats, stop talking. Also, just to remind everyone about the photo policy, please don't take photos unless you have permission. And for all those that aren't aware by now, this is the Build It room, and I have a few giveaways. Is everyone familiar with Security University? They're giving away some free classes. Anyone interested in a free class? I do have some tokens I'm passing out. For those of you that sit closer, tend to get more swag. I can try to... Oh, it's a little bit too far.
I'm really close.
There you go. Also, I just want to make a quick announcement about the party tonight. The party is going to be at 9 o'clock. It's going to be right behind us in this room. Entrance to the party is from the terrace level on the back side here. All of the beer is going to be free until midnight. And then after that, it's going to be cash only. As you enter the party, they'll give you a ticket for mixed drinks. Also, the party is over by 1 o'clock, and it should be a lot of fun. I also have, if anybody would like to enjoy some M&Ms, we got a bag of M&Ms. Share them. All right, we're going to go ahead and get started with the talk. It's tap on, tap off, and we're going to turn the time over to Kristen Green.
Alrighty. Thanks. Can everybody hear me? Yeah. Yes? Excellent. Slightly more artistic version of the title slide. Thank you, Josh. First, of course, we have to start with a standard NIST disclaimer, not endorsing any products, of course. Now, just so you know what you're in for today, I'll start out with telling you a little bit about myself and my co-authors. In other words, why you should listen to me for the next 45, 50 minutes. Tell you our purpose, our research goals. Definitely want to focus on usability background because I think that's something this audience is perhaps a little less familiar with. A little more? Oh, let's do this. Yeah. And then, of course, password security background. You guys are obviously more familiar with that. Talk to you about some relevant prior work that motivated the current research. Talk about our current methodology and results, and of course, wrap up with some conclusions. So I'm Kristen Green, cognitive scientist and usability researcher in NIST Information Access Division. My co-authors in the front row, not paying any attention, Joshua Franklin and John Kelsey. They're both in the computer security division. One's a cryptographer, the other information security engineer. So how did this current project get started? Well, we met a few years ago on the voting project. I was working on usability, they were working on security. And then fast forward a year or two, I'm into the usable security space, but really just looking at usability. Then one fateful day in the NIST cafeteria, I asked what I thought was a very simple question. How much security would I lose if I permuted or rearranged some pre-existing passwords to be easier to enter on mobile devices? Naively, I thought this would be a very short answer and our project would be done, in a week or so. A year, something later, here we are today. Now, to be fair, that entire year wasn't spent, writing code and actually answering the technical question. We had to spend a lot of time learning to speak each other's language. And so one of the things I want to make sure to convey today is that sort of usability lingo, because it's really important that we have usability and security people working together. And to do that, it's really helpful if you can actually understand what the other party is saying. So here's the problem in a nutshell. You have this password. And okay, let me start with, at NIST and many large enterprises that are concerned about the security of their enterprise, they force you to change your password very frequently. It's very annoying. And they'll make these password suggestions that are really nasty and look something like this, which is 12 characters long, but it actually takes 23 taps on a mobile keyboard to enter. So you're effectively doubling the length of the password just because you're now entering it on a mobile device. And that's because of all the keyboard changes that you have to do, right? You can't get to all the keys from a single screen. You now have to switch back and forth between them. Now, if you take that same password, rearrange it, permute it, so that it's like characters are grouped together, it's the same length, it's composed of the same exact characters, but now it only takes 15 taps to enter, right? So that's the problem in a nutshell and the solution. And I should be clear that right now we're talking about system-generated passwords. User-generated passwords are obviously very important too. So the purpose, larger purpose, is to explore the current state of usability and security metrics for passwords. So we wanted to assign strength metrics for passwords for which we already had usability data. So we've run a series of several studies. I'll talk about those a bit later, but they were usability studies, and now we want to add the security component in to measure the security of those passwords. And again, I already said what the question was, but how much entropy is lost as a result of permuting passwords to be easier to enter specifically on mobile devices? So usability background. Pay attention for this part. You can sleep through the password stuff. When you think usability, you should be thinking about several different things. One is context of use, and this is sort of an overarching concept that's really important. You have to know the context in which your users are performing tasks with various devices. Now, effectiveness, efficiency, and satisfaction, these are really important, and this is what we measure. And this is a measurement institution. We're really concerned with measuring things. Now, I didn't just make this up and pull it out of my hat. There's an actual ISO standard, ISO 9241. It's like a big old 20-part standard, but this is really what you need to focus on. Right? The definition of usability is the extent to which a product can be used by specified users, so you need to know who your users are. Are they programmers or are they regular Joes? So specified users to achieve specified goals. You have to know what they're trying to do with your product or system. To achieve effectiveness, efficiency, and satisfaction in, again, a specified context of use. Context of use is pretty self-explanatory. Here, we're dealing, obviously, with the mobile context. Desktop versus mobile, two totally different worlds. Bless you. Effectiveness, the accuracy and completeness with which users achieve specified goals, again, from this ISO standard. This is generally measured via error rate. So when you're thinking effectiveness, you are thinking wrong versus right. And you can measure errors at different levels of granularity. We'll talk about that in a bit. Efficiency, resources expended in relation to the accuracy and completeness with which users complete their goals. Right? And this is generally measured via time on task. So in terms of passwords, we can look at it by password entry time, but we can also look at the number of keystrokes or taps that it requires to enter the password. And that's what this talk is about. And I should mention that there's often, as in many areas of life, there's a speed-accuracy trade-off function. So when users are trying to be more accurate, they generally have to slow down. So satisfaction is freedom from discomfort and positive attitudes towards the use of the product. I would love to see somebody who has positive attitudes toward the use of passwords. These are generally measured via standardized or customized questionnaires. But I really want to emphasize that you don't just go making up questions willy-nilly, right? There's an entire field of questionnaire design. You have to be very careful when you're asking users what they think about a product or a system or whatever, because you can very easily bias them, right? So you have to be very particular with your language. So if you're thinking about, doing some type of usability study, try to get the right people to help you design your instruments. Questionnaires are also called survey instruments. So the first two that I talked about, effectiveness and efficiency, those are the objective usability metrics. They're pretty easy to measure. Satisfaction is more subjective, obviously, but there are still objective ways to measure it. And that's what I want to make sure to point out here. So, and one thing I thought was interesting when I started working with these guys, I'm like, wow, there's kind of a little parallel thing going on here, where usability, we talk about effectiveness, efficiency, satisfaction. And you guys talk about this confidentiality, integrity, availability. But across both fields, context is really important. Like I was saying, you have to know the user context, the context in which your user's using, the product. But you guys are always talking about, well, it's only secure for a given context and a given threat model, et cetera. So I really think there's some nice parallels there. So password security background. So there are many classes of attacks on passwords. You guys are probably more familiar with them than I am. But I want to point out here that we're really only concerned with password guessing. That could be brute force or intelligent guessing. Actually, let me rephrase that. We are concerned with all of those things, but in the current work, we only are talking about password guessing. So password strength is often expressed in terms of entropy, which is really only loosely related to the term as it's used in thermodynamics. So entropy was originally defined by Claude Shannon back in the 1950s. And there are two main password metric groups. So it really depends on whether or not they were generated by a system-generated or randomly generated passwords versus user-generated passwords. And you need different metrics to measure different things. So the Shannon entropy formula is H, base 2 log of B to the power L, where H is the total entropy, And B is the number of characters to choose from. So it's like your starting character pool. L is the password length. And I should note that there are modified versions of this out there, but we're just talking about regular for right now. So let's talk about some Shannon entropy examples. I didn't just pick these passwords from nowhere. These are actually the 10 passwords that were used in a desktop and mobile password study, usability studies at NIST. So that's why it's really interesting that now we're actually looking at the security of them, not just the usability. So you can see here these passwords are ranging from in length from 6 to 14 characters, and the entropy ranges accordingly, from about 40 all the way up to 90 something. Now, user-generated password metrics. There's guessing entropy and there's min entropy. I see you. So guessing entropy is the estimate of the average amount of work required to guess the password of a selected user. So you're trying to get a specific account here. And it uses Shannon entropy as the foundation and then measures password strength based on a rule set. Min entropy is the difficulty of guessing the easiest single password to guess in the population. So you're not targeting a specific user here, it's just whatever's the easiest password to get. And this specifies dictionary tests and password histories as heuristics to try to ensure at least 10 bits of entropy. Entropy is measured in bits, forgot to mention that, but you probably already knew that. So NIST Special Publication 863, Revision 2, has some entropy heuristics here. So a rule set, basically the first character, you get 4 bits of entropy, second through the 8th character, you get 2 bits per character. The 9th through the 20th, you only get 1.5 bits per character, and then 21 and up, you're only going to get 1 bit per character. And then you can get like a bonus, 6 bits of entropy, for adding some uppercase and adding some non-alphanumeric characters. You can also get a 6-bit bonus for having a dictionary check. There's a min entropy rule set as well. So you have to search a dictionary of at least 50,000, obviously more is better, but at least 50,000 words for the password. If found, obviously rejected. And passwords that are detectable permutations of the username, not allowed. So now, what I think is more interesting is our research and results. Let me start with the prior work that actually motivated my current question. So we had, as I mentioned, a recent behavioral study on mobile password entry. So people had to use iPhones and iPads, iOS, and they had to learn, enter, and then recall 10 randomly generated passwords. Those were those passwords I showed you a few slides ago. And what was really interesting here is that in comparison to the previous desktop study, we actually had people who A, couldn't finish the task, and B, who dropped out. I have run many research studies. I've been doing research since I was an undergrad. I've never had anybody drop out of a study when they're getting paid $75. It doesn't happen. But we literally had people who came in. They took a look at the second password, and they said, this is not worth the money. That's how bad it was. And that's why I thought there has to be something better. We have to start considering the mobile device constraints when we're asking people to have and generate these crazy passwords. So sorry, sidebar, but that is such a huge finding, even though it's not, it's not a statistical effect. But the fact that we had people dropping out is huge. Also, we had people who stayed past the allotted hour and a half. They persevered, they're trying. 2-hour mark, they still hadn't finished the study, all right? In the desktop, people didn't take longer than an hour, all right? So this is a big difference. And we found that the on-screen keyboard switching, again, that changing between the different keyboards is really what's impacting the difference between desktop and mobile. And of course, that significantly increased the input errors, increased the input time, and reduced satisfaction. So basically, across all 3 components of usability, it is much worse. So let's talk about measurement granularity for a second, because that's one of the big advantages of doing laboratory experiments. And unlike, what's her name, Alyssa, her talk last night, I'm not allowed to do research in bars. So this was a real laboratory study where we brought in like 160 actually people, and they come into the laboratory, it's hands off, they have to sit with the device, and we have a data collection program that actually collects the data. And that is available up on GitHub if you're interested. So the password level is one level of granularity, but then you can go down to the individual character level. You lose some information if you just look at the entire password, right? If you say, okay, the entire password either fails or does not fail, it's accepted, you don't know if it failed, did it have 1 error, or did it have 10 errors out of 12 characters? Like, you're missing information there. So when you can capture that extra level of granularity, you really should go for it. So at the character level, you can have different types of errors. So you can have things like omissions, you can have extra characters, you can have transposition errors, you can have just straight up wrong character errors. And what's really unique to passwords is that you can have a specific type of wrong character error like 0, 4, and O, right? This doesn't happen in general text entry research. And I want to point out that we're not reinventing the wheel here. When I'm talking about measuring things at the character level and errors, people in the human-computer interaction field have been doing this for decades. So this is pretty well established. Like this went back to the expert typing, the transcription typing studies, back when they actually had real typewriters. Okay, so this is a real thing. And so again, it's important to look at the nature of the error as well as the number of the errors, because understanding why people are making the errors they are tells you a lot about what's going on cognitively. So these are data from the previous study I was mentioning, and immediately should jump out, even before I put up the green highlighting, that more errors relate to tiny keyboards. Why? Because the adjacent key error, that particular error type, was where the biggest difference between platforms was. So there are only about 500 errors in the desktop study total. Contrast that with about 2,100 in the tablet study. And then, 1,200 in the tablet study, and 2,100 in the mobile study with the smartphones. So basically, smartphones have 4 times more errors overall than the desktop study did, and tablets had about 2.5 times more errors. So just changing the device is impacting people's ability to input passwords dramatically. This is huge. So let's talk about on-screen keyboards for a second. Don't worry, you don't need to actually see the characters on the keys. But just want to point out that there is some similarity between major operating systems, right? You have iOS, Android, Windows. They all have this sort of 3 keyboard screen model, right? And this is a really big difference from desktop, where you have all of the keys available all the time. There's actually a standard, ISO standard, that specifies desktop keyboard layout. There's no such thing for mobile keyboards, and I'm not suggesting that there should be. Flexibility in programming and design is a fantastic thing, but it does make research with them a little bit more complicated, and it also means that it's a big deal, the fact that there are these 3 screens. And across operating systems, obviously you guys pretty much all have smartphones, I'm assuming. It's grouped into kind of the letters keyboard is first, the first screen depth. You can think about them in terms of increasing screen depth. Letters, numbers, and then the funky symbols on the 3rd screen. So up close, screen depth 1. What's really important here is that you have these keyboard change keys that let you get to the 2nd and 3rd screen depths. Side note, back to the mobile study for a second, we actually had a participant who did not know how to get to the 3rd keyboard screen. It's funny, but it's not. Because if people don't even know how to get to the 3rd keyboard screen, do you think that when they're generating their own user-generated passwords, they're using any of these characters? No. What that means is then you have a lower starting pool of characters to choose from. So you're already limiting your entropy. So current work. How am I on time? Good. So we defined a password permutation that divided passwords and divided the characters up into 4 distinct classes. Right? So you have uppercase, lowercase, numbers, and symbols. And you always want to group that, at least for our permutation, you want to group them in that order so that you're essentially following the order of the on-screen keyboards. So an example would be 5C2'QE would then be permuted to QCE52'. And notice that we've kept the order within a character class constant, and that made our calculations a little bit easier. So what are some results? All right, let's talk about tap counts. Now, tap counts, as I mentioned before, is measuring one facet of usability. That's efficiency, so the time to enter a password. Now, obviously, for password, like real passwords in the real world, effectiveness or error rates are really important, because typing something in incorrectly is what gets you locked out of an account, right? You don't generally get locked out for typing too slowly. So why then are we talking all about tap counts today? Well, a couple reasons. The most important is which we didn't actually need human data to do this part, right? Because you can count the number of keystrokes or taps without having humans involved in it at all. Obviously, we need human data to look at error rates and satisfaction, and have a recently completed study that I won't be covering today, but hopefully maybe next ShmooCon. All right, so permuted password, original password is on the leftmost column, followed by permuted password next to it. These are a subset of the 10 passwords from the previous studies I was talking about. These are just 5, but you can see they range in length from 6 to 14. And the next column, you'll see taps. The original, so the number of taps for the starting password, followed by the number of taps for the permuted password. And then keyboard changes is what's really important here. Again, you'll see original followed by permuted. And then the tap savings doesn't sound like too much, right? 1 to 7 taps, depending on how long the password was. Well, if you think about how many times a day you would have to enter this password, that's a lot. People are sensitive, there's a lot of research in the psychology field, people are sensitive to very small inefficiencies, right? So this is actually a big deal. The other thing I really want to point out is that it's not actually just length that predicts the number of taps that will be saved. It really depends on the number of on-screen keyboard changes that were in the original or required in the original password. That, in turn, depends on the number and the frequency of those special symbols and obviously the numbers, because those are the types of characters that require getting to those second and third keyboard screens. Now, we have the issue with this permutation idea of password collisions, where you can have multiple distinct passwords that are all mapping down or colliding with the same user-friendly password. So this gets into our first experiment. I'll be talking about a series of 3. This is where I have to thank my wonderful co-authors, because they were the ones who wrote the Python code, did these Monte Carlo simulations, and helped actually answer my question. So why aren't you up here presenting then? I'm just kidding. So our first question, how many how many passwords collide with the same user-friendly password? So how many collisions? Here you'll see length on the left, ranging again, this is from 6 all the way to 20, and then 10th percentile, 90th percentile, and average. And so what you want to look here, say if you just look at the top line, ooh, I do have a laser pointer. Now I can use this for something other than playing with my cat. All right, so you're ranging here from 120 to 180. But now if you look down at length 10, it's going all the way from 5,000 to 25,000. Now, if you look down here at length, say, what am I looking at, 14? No, 16. Like 2.5 million all the way up to 40 million. So you can see that there's a lot of variability there. So experiment 2, entropy loss. How much entropy is lost by doing this password permutation? So this was really the heart of my starting question that I thought was going to be so easy to answer. Silly me. Here are the results. So length again, left-hand side, ranging from 6 to 20, 10th percentile, 90th percentile, mean, and I should say this is entropy loss in bits. And then the last column is particularly interesting because it's how many additional lowercase letters would be needed to get back to that starting point of security. So essentially, we're losing some security by doing this permutation. How much do we need to add back with all lowercase letters, because that's the easiest thing for people to type on mobile keyboards, to get back to that starting point of security? And so you can see here that the average entropy loss ranges from like 7 to 31, and additional letters required ranges from like 2 to 7. So our third experiment, all lowercase. This prompted us to ask, well, what if we didn't have to do these crazy complex passwords in the first place? What if we could just have a longer, all lowercase password? Wouldn't that be easier to enter on mobile devices? Yes, it would. If we could get the IT people to go along with it, and of course prove that it is equally secure. So, from left to right, complex password, what it would have to be if it was all lowercase, and the extra letters that would be required. So, for instance, what was a length 6 complex password, with numbers and symbols. Now you're going to be looking at like all lowercase password of 9 letters, so 3 extra letters there. So like if it was 10, now you're looking at all lowercase of 14. And here's an example of that. I believe this is, if I counted correctly, 10, length 10 on the top, so that's that crazy password, one of the ones we used in studies. And then if you were to replace it with like a length 14 randomly generated, but all lowercase one. So in the top, I'm not going to be able to remember, 23 taps? Somebody check me or not? But the second one is 14, but it only requires 14 taps, right? Because there's no keyboard changing involved, and that's the important thing here. So now it's time to see if you guys are all paying attention. Unholster your phones. I want to see movement. Okay. Now try to type this. This will drive home the point like no other. I'm looking at you guys in the back. You think I can't see up here, but I can. Okay. I see some phones, so I'll go ahead. Yeah, thank you, yes. So unholster your phones, try to type this. On an iOS device, right, it's pretty brutal. You're gonna type M, keyboard change, another keyboard change, hashtag. Keyboard change to get back to the letters keyboard, an O. Keyboard change to get to the number kind of common symbols keyboard, type your right parentheses. Keyboard change to get back to the letters keyboard, FP. Keyboard change, another keyboard change to get all the way to that third screen depth and type your caret. Keyboard change to get back to the numbers. I'm not gonna go through the whole thing, right? You get the idea.
It autocorrects to some level.
Oh, wow! We had autocorrect turned off in our studies. Yes, and that is one issue with passwords as well. You know, people are pretty fast at typing like these text messages. You just see them whizzing along, right? Question, yeah.
Like, but the thing is, at least with Android and iOS, I don't use iOS, but Android has custom keyboard like Squeaky and stuff, or they make this, I did this in 4 types.
That's awesome.
So like, did you take those into your calculation?
No, we're only doing iOS here only because that was the operating system that we had used in previous research. But yeah, absolutely, and we thought about that, so I'll talk about it later, but we have this big old document that's not quite published yet. But one of the things, yeah, it's like 52 pages, still getting through the review process at NIST, but one of the things we talk about in there is that, you know, different operating systems have very different constraints and opportunities. So I'm so glad you brought that up, thank you. That's very true. There are and that's one of the things I was talking about with the fact that there's no one standard on-screen keyboard means that you have some operating systems that get to have these cool, crazy, nice keyboards, and then some that unless you jailbreak it, I guess, can you even do that and put a new keyboard on? Sure, you can do anything. But you know, it really, really depends a lot. There's a lot of variability there. So we started with iOS, and that's what we were sticking with just for now, but absolutely other platforms are really important and have different keyboards. All right, so now I hope you didn't put your phones away yet. Get them back out if you did. Try to type this, and you will see why this password permutation idea makes your life so much easier, right? Shift key R, MOF, PAF, one keyboard change, 2207, another keyboard change, another keyboard change. What you'll notice if you're using an iOS device is that this password actually could be better optimized, this permutation, because you could reorder the order of the last few symbols, because the parentheses on an iOS keyboard are actually on the second keyboard screen, and so if we had moved that over, then we would have saved you know, an extra keyboard change. So anyway, yeah.
That one does not pass some of the DoD complexity rules, too many things in the same string.
Aha! I'm glad I'm not DoD. Too many. Oh, sorry, let me repeat the question. And the original question was about Android keyboards. I'm sorry, I forgot to repeat that one. So his point was that this password would actually not pass DoD password requirements because there are too many things in the same string. Did I get that right? Yep. And so this definitely isn't going to work in all contexts of use. But that's a really good point. And you know, there are different password requirements for different enterprises, and obviously personal accounts are even different from that. And so, you know, this is one idea. So just to recap, it's not on the slide because I don't need a slide for this one. Usability. Think context of use, effectiveness, efficiency, and satisfaction. And you can actually measure, and you should measure all of those things. Entering complex passwords on mobile devices is really hard, but we love our mobile devices. Like, we need to find a better way. Our password permutation makes it easier. We precisely measured the security loss and fixed it by adding a couple extra letters. So device constraints, if you haven't gotten it by now, this is like one of the main take-home points. Device constraints matter a lot for usability, right? They also matter for security, right? If you give people systems that are too hard to use, they will find ways around it, right? If people don't want to log into their work device, what do you think they're going to do? Start being tempted to use their personal devices, and we probably don't want that. Old password policies kind of play very badly. They do not play nicely with newer devices because they're really not taking into consideration the device constraints. And if I haven't said it enough, I'm going to say it one more time. Both usability and security matter, right? We have to work together on this or we're not ever going to get anywhere. And I think that's one of the main things that I really want to drive home is that you know, it's possible to work together, and it's actually been kind of fun, I must say. And that you really do need to consider both of these, because only by measuring passwords along both dimensions or any facet of usability, you could, you know, measure the usability of the crypto libraries that they were talking about in the previous talk, right? You know, how efficiently can people use them? How effectively can they use them? How happy are they when they're using them? You can measure usability, and you should, because only by understanding how it interacts with security can you really hope to get anywhere. So all of our code is available on GitHub. We have US NIST Gov GitHub website. If it's not up there already, it should be up there soon. Just keep checking back. Sometimes it takes a little while in government. So the password metrics and then a data visualization tool. Because once you actually start measuring these different components of passwords, you can measure the keystrokes, the error rates, you can measure the security. Then you can start doing some cool things like actually looking at them side by side and seeing how changing one affects the other. So we do have a data visualization tool. I decided not to tempt the demo gods and try a live demo at my first ShmooCon presentation, but I do have some screenshots if you want to see them. Oops, oh dear. The data viz tool, there we go. The data visualization tool is actually a summer undergraduate research fellowship project by Catherine Plone. If you guys are undergrads or you know undergrads, you might encourage them to look into NIST Surf project. It's pretty cool. And for questions, you can talk to me. If there are security questions, please ask a really hard one because I'm punting to my co-authors. You can find me in the Information Access Division. They're in, again, the Computer Security Division. And as I mentioned before, we do have a really nice big document typing up all of this stuff. It may or may not be out before the ShmooCon proceedings. You know, again, it takes a little while.
Especially on a mobile keyboard.
Yeah, especially we wrote the whole thing on a mobile keyboard. And acknowledgements and take questions. I certainly can.
Yeah, so,
Yeah, you can't get out of it that easily. Yay, fun. And don't forget to repeat the question.
Okay, so the question was basically if we'd taken into account the fact that people could look at the algorithm that was used to generate the passwords or to permute the passwords and use that to make their search more efficient, right? And so the point is, when we did the calculation, we worked under the assumption that the attacker knew the algorithm. They knew we're talking about randomly generated passwords to begin with, and so we know the attacker knows the algorithm that was used to generate the passwords. Often you'll have these weird things where you have randomly generated passwords, but then you still have rules that don't even make any sense for randomly generated passwords, like if there's a 3-letter dictionary word in there, you have to reject it and try again. So you actually lose entropy by trying to make it stronger but not knowing what you're doing. But you know, we take that into account, and then we take into account for the permutation. We assume that the attacker knows what permutation we're doing. That's why we're looking at the collisions, the number of different system-generated passwords that all wind up at the same place at the end. And we can say, well, now you can only search one of those instead of searching all of that key space. So does that make sense? Okay. So ask more questions.
Yeah. Oh, okay.
One of the issues that we have on training users is not to do stupid stuff, because it's easy to do stupid stuff.
Bingo.
So you touched one point of passwords and mobility, which is very valid, but it's very limited. In security, we have way more problems that are their cat name as part of the password or this password. So how much do you think we can use cognitive techniques to make it easier for people not to
The question was, how can we, and correct me if I didn't hear it correctly, how can we use cognitive techniques to make sure that users are essentially not doing stupid things and there are, what is that? Oh, yeah, it's mine now. Just kidding. No, it's okay. And that's a really good question because, as he mentioned, we're only talking about one particular piece of passwords here and improving that, and that people, as you said, people are doing other stupid things, like writing them down, or which may or may not be stupid depending on where you keep your, handwritten notes. But things like using their cat's name or their username and such as that. And unfortunately, user training and education can only go so far. Some people simply don't get it, and it's really hard to make them get it. It is possible to explain things to people, and yeah, you can do some training, but fundamentally, people, their main task is not logging into a computer or generating a password. They have a larger goal. They're trying to get their work done. They're trying to go, create an account just so they can buy something or do something. And so it's really they're just doing whatever they can to get past it. And so you can look at some like the task interruption literature in psychology and such, but I really think that we need more research, honestly. And people have been doing a lot of research on passwords and stuff, but actually looking at it from that true cognitive psychology standpoint, I think is a really interesting way to go. Yes?
Suggestion for a follow-on might be to see if users prefer like a one-time password fob to a longer, single character password, because at some point, I'd much rather get a text message that I have to then type in than I would, try to get a 15, 20, 25 character password.
The question was, or a suggestion was that an interesting idea for a follow-on would be to see if people would prefer like a one-time fob with a really short pin over these really long, 20-character passwords. And I agree absolutely. And one of the things is how well people understand these one-time pin issues, if they're willing and to get things text on their mobile devices. And I think that's a really, really important avenue of research because let's face it, we all want the password to die. I mean, there's an entire, NSTIC, National Strategy for Trusted Identities in Cyberspace, right? They're all about killing the password, but unfortunately it's going to take a while. And in the meantime, if we could do some of these things, like have one-time fobs, I think it's an excellent idea. Then you wouldn't have to manage so many passwords either. Yes? Exactly, it could be all numbers, which you could do from all one keyboard, no keyboard changing allowed, are required. And the all numbers idea actually has an interesting side benefit, is for people who are not very fluent in English. I work with a lady from Taiwan at work, and she is telling me that her mother actually, and a lot of international people prefer to use passwords that are all number-based. So it's a cultural thing, and language definitely numbers are easier. Yes? You again. It's good.
Well, so if you're receiving a one-time password through like email or text or whatever, you can just copy, using your mobile text, you can just copy paste it, so it doesn't matter how many characters it is. So why would they prefer a shorter password?
I believe that you were talking about a one-time fob, like an actual device that has a short thing. And so, yes, if it is coming through text message or email, then theoretically they should be able to copy and paste. But if it's something that's actually on a hard device, then they've got to transcribe from device to thing. Yeah, so in one case you're right, other case not.
And also sometimes the paste is disabled.
Yeah, thank you so much for saying that. Also, sometimes the paste is disabled. And you copy and paste on mobile devices does or does not work so well. Yes?
Have you studied, or has anyone else studied the effects of password hiding on error rates?
Password hiding?
So the concept where the OSs will hide everything but the last character you entered?
Yeah, I mean, interesting. Oh, so the question was, thank you. So the question was whether or not people have studied password hiding. So where the OS will hide everything but like the last most recently entered character. I actually don't know who else has studied it, but I do want to mention that in our original study, the mobile study, we thought that we would be super secure and we would turn on a setting that many people don't know exists, which is that you can turn off the capability to actually even show it for a split second. So we thought, we want to make this as similar to the desktop study as possible, right? In the desktop study, people are typing, they only see asterisks, you never see what you're typing, so no visual feedback, but you do have tactile feedback, right? Because you can feel which things you're typing. But in the mobile study, we thought, oh, well, let's make this secure setting, we'll turn it on, so that it's similar to the desktop where people can't see what they're typing at all. Upon retrospect, that was extra mean to the participants, but it also is not what most people are really doing in real life. Like, a lot of people don't even know that this setting for their keyboard exists, and so it was a little unfair to do that, and I think that if we were to rerun the study with that setting off, that we are on, we would get slightly different results. It would be a little bit better.
I wonder if you took it farther the other way, like revealing 2 to 3 characters when they're something.
That would be wonderful. I don't know how we could do that without writing like a special application, but hey, I know some people who code. We should do this. Yeah, thank you. Yes?
I may have missed it mentioned, but do you plan on studying the effect of your optimized passwords on error rates or lockup rate on your study?
The question was, do I plan on studying the effect of these optimized 10 minutes, optimized passwords on error rates? And the answer to that is yes. Recently completed a cross-platform study where we used a subset of these permuted and original passwords. It was within subjects, so we had all people using a smartphone, a tablet, and the desktop, so we could really compare, of course, counterbalance order, all that good stuff. And I haven't finished running the inferential statistics on it yet, but just looking at the descriptives and the qualitative data, it definitely, people are faster to learn those permuted, easier passwords. They're making fewer error rates, able to better recall them, and they give them way higher subjective satisfaction ratings. So, yes, good question.
Did anybody walk out?
Nobody walked out. It was great. I was really worried about that after the first time, because of course it extends the amount of time you have to run your study for. But nobody left. I will say not everybody completed the study, and I think that was in part because we're having them use 3 devices, same set of passwords on each. Now, it was many fewer passwords, just 4 instead of 10. But we also had them do a baseline typing study. So in the text entry literature in HCI, there's a corpus of like 500 phrases that they've used across the years. And so we really wanted to so we pulled from that to do a baseline typing study because we want to see how proficient are these people at just typing regular phrases compared to these really crazy passwords. And that was one thing we hadn't done in the previous studies, and I think that's an important addition. So you can kind of say, man, this is a super user, they type, however many words per minute, but when you ask them to type these passwords, they slow way down. And I think that's really interesting to show that it's not just about familiarity with the keyboard, there are these constraints of passwords themselves that are hard. Do I have time? Was that 10 minutes like to stop, or? Okay, next. The question was, have I looked at it from the other end, where seeing the key space that people are choosing from to generate passwords on mobile devices? Did I get that right? That is an excellent question. We actually, and I'm not the first author on this, but somebody at NIST has recently completed a user-generated password study where they actually gave people different password rule sets and had them generate as many rules as they can. And my immediate thought after that study was, oh my God, can we please do this on mobile devices? Because what I would really, really put big money on is that people are not choosing from the entire character set. And in fact, I don't want to give away too many of the results, but we're finding that already with the desktop. Some keys are just more frequently used than others. And I imagine it has something to do with their frequency in the English language. So we're planning to get some linguists involved as well. Good question. Yes, you again. Okay.
When keyword was created, the idea was that's going to slow down everybody so that the mechanics doesn't get hurt when you actually type, right? That's what you created with current.
Hard keyboard, I thought it was actually because on the old typewriters, the very commonly used keys, they tried to actually spread those out so that the things that are coming up and hitting the paper. Oh, is that what you're saying? Sorry, I couldn't hear you.
But when the mechanics just slow down people so that the mechanics would actually be able to go along. Of course, today we don't have this problem, but that's not the problem. The notion is, and you pointed out there are 3 different ones. Could we actually design one that's meant to allow people to do crazy that fast?
That's a good question. So the question was whether or not we could design a keyboard that was specifically intended to allow people and support them to do these crazy passwords faster. Yes, I would love to design such a thing.
That's unlikely to be extended because the Thorax has been around for years and people don't accept it.
Yes, that's a good point. He said that's unlikely to be accepted because the Dvorak has been around for years and people don't accept that. There is a better, faster version of the keyboard than the QWERTY out there, the Dvorak. Thank you for bringing that up. And people don't accept it. You know, QWERTY is too far entrenched. And that may or may not happen with the mobile, Mobile is new, but also, as that gentleman was mentioning, you already have the capability for these customized keyboards, and there's a ton of them out there. So people are willing to get different keyboards for different purposes. I wonder if it would be possible and helpful to have like a password entry keyboard for mobile devices. Because when you think about it, on a mobile device, the keyboard is intentionally small so that you can see what you're doing on the rest of the screen. When you're typing a password, you don't actually need to see the rest of the screen. Maybe one line at the top if you're able to even see the password, the letters, right? So you can imagine designing a keyboard that took up almost all of the smartphone screen, left just a little place for you to see what you're typing at the top, and where you could have almost all of the letters, or at least a larger subset of them, available at one time. And I think that would be awesome. Yes? The question was whether or not if I've looked at any research on cognitive dissonance while typing a password in. I have not. I think that would be quite interesting. Right, and so he was saying that the cognitive dissonance, where people have to now think about what it is, where the letters are, and what they're typing, and it obviously slows them down. Yeah. 5 minutes? Still have more? Yes?
Yeah, so I don't know if you mentioned this at any point during your presentation. How do you envision people using this? I know a lot of people don't actually generate their passwords randomly as you would demonstrate it. And when they are required to use a special character to do it, like you mentioned, as
Put a bang on the end.
yeah, I mean, it's common characters as well, special characters. So in what context do you envision people using this, and how do you anticipate it having most impact?
The question was, in what context, how do I envision people actually using this, and where would it have the most impact? Did I get that right? Great. Because a lot of people are not using, randomly generated passwords. They're making up their own, and they're already generating them with, the symbols at the end or something like that. I would love to see something like this implemented in our enterprise password suggestion system, right? When you go to create this new password, you get this crazy suggestion, and it has nothing to do at all with how easy it would be to enter in a mobile keyboard. And so rather than what we did here was, take these originally generated keyboards, permute them after passwords, and permute them after the fact to make them easier. Why don't we just have a password generation algorithm that makes them easier from the get-go? And that's how I would see it being used in the real world. Or there have been some people that have said, well, what if you had like a little piece of system-generated password that then the user can do, add on their own bit with. And I think that if you were going to do something like that, something like this could help there too. But you mean you want somebody to actually use this? Yeah, it would be cool. Yeah. That's a really good question. He said, have I studied the difference in errors between the horizontal and vertical orientation of the smartphone or tablet? In the original study, in order to make everybody do the same thing, we actually had them limited to the the vertical orientation, so portrait orientation. Absolutely, that matters a lot because key sizes differ more so on the smartphone. If you flip it, obviously they get bigger. In the follow-up study I was mentioning, we allowed people to pick their preferred orientation. And so there I do have some measures, but again, not written up yet, of whether horizontal or vertical matters, and it does matter. And what it does is it reduces the instance of adjacent key errors because the surrounding keys, they're bigger, right? So you're not making as many of those motor execution errors. One more? Yeah, okay. No? He was waving at someone, okay. Yes?
Speaking of the death of passwords, have you heard of anything about Squirrel? Any thoughts about that?
Squirrel. I am not familiar with that other than the big fat ones on the NIST campus.
SQRL, basically, it's not fully implemented yet, but it displays a QR code on a web page
So the question was about Squirrel, where you display a QR code on the web page, take a picture of it with the app, and then you're logged in. That is pretty cool. That does look pretty cool. No, I'm not familiar with it. I'd love to check it out. Thanks for mentioning that. And that would be a nice usability study to do. You know, can people understand this? Are they, you know, accepting of this? Because sometimes you run into this issue where you have fixed this really cool problem, and then people don't actually understand, and they are not welcoming of that new technology. So, and education plays a big component there. That would be cool. Thanks. Yeah, done. Okay, thank you.